name is Myron.
My name is Lyndon.
And I'm Ryan.
And this is our OPTI380A Lab report on lasers with Harsha Pradeep as our TA. So for an overview of the experiments, in part A, we use a laser cavity alignment to align a laser cavity and observe different modes. In part B, we use a Fabry-Perot spectrometer to analyze longitudinal modes and verify the free spectral range. In part C, we use an optical spectrum analyzer to record intensity versus wavelength of a laser and a diode. And in part D, we use an electrical spectrum analyzer to relate the observed beat frequency to laser cavity length. So in part A, we used a helium neon gain tube with a green alignment laser and adjusted the mirrors and the iris to align the cavity. Once aligned, we adjusted mirror M, as noted in the photo, to observe different modes. So in mode 1, we had the max intensity when they're overlapping. In mode 2, we had 2 circles. And in mode 3, we had 3 circles, with the central one being the brightest.
Going into part B was the Fabry-Perot spectrometer, where we aligned a laser into a Fabry-Perot cavity, measuring the output on an oscilloscope. And so with that output, we found the free spectral range, the individual mode separation, and the longitudinal mode spacing. And so we found a FSR of 1.56 milliseconds, individual mode separation of 940 microseconds, and a longitudinal mode spacing of 0.9 gigahertz, which is a little different than theoretical due to our measurement of the laser cavity. And so going on to part C, which is the optical spectrum analyzer, where we aligned a laser or laser diode into the OSA input, switching the output onto high resolution mode using the Thor Labs program on the laptop. We found the central wavelength, the mode width, and the mode spacing. And so the results of this turned out to be the wavelength of the helium neon laser was 633 nanometers, the laser diode was 651, and then the mode spacing of the helium neon laser was 0.002 nanometers, with the laser diode being 0.2 nanometers.
In part D, we used an electro spectrum analyzer to measure the longitudinal mode spacing of the laser. So first we physically measured the laser cavity to estimate longitudinal mode spacing, and then we used the spectrum analyzer to find frequency peaks. We only found one frequency peak, so we just compared this to our theoretical value. So our peak was at 706.3 megahertz, and we compared that to our theoretical value, 655 megahertz, which was an error of 7.8%. So to summarize, we successfully found everything that we were looking for. Our sources of error were primarily misalignment of mirrors, inconsistent power supply, stray light, and the physical laser cavity measurement. And this experiment will help us in the future to understand how lasers work. Thank you.